Subscribe to the channel so you don't miss out on any of these videos. Imagine a scene in space that stretches across vast, silent distances, an almost infinite void dotted with stars and punctuated by bright planets. But hidden in the shadows of this cosmic canvas are tiny, floating particles that rarely capture our attention: space dust and cosmic debris. These unassuming specks play crucial roles in shaping the universe and have an influence on everything from the birth of stars to the existence of life on Earth. Though often invisible to the naked eye, cosmic dust and debris weave a narrative that impacts planetary systems, influences the evolution of worlds, and challenges our ability to observe the universe with precision. Join us as we delve deep into the mysteries surrounding space dust and cosmic debris, examining their origins, compositions, and the powerful forces they wield over the cosmos. Space dust, known scientifically as cosmic dust or interstellar dust, exists everywhere throughout the universe. This dust can range from microscopic particles to slightly larger fragments that travel through space with no defined path. Formed primarily from the remnants of ancient stars, these particles drift freely, occupying vast spaces between stars, planets, and galaxies. Cosmic debris, meanwhile, includes the larger objects found in space, such as meteoroids, asteroids, and fragments from comets that orbit within solar systems, some of which occasionally make contact with planets. Together, cosmic dust and debris interact with gravity, radiation, and other forces that ultimately impact planets and stars in remarkable ways. Cosmic dust can be traced back billions of years to the earliest stages of the universe. The dust that floats through interstellar space today includes remnants from the explosive deaths of massive stars, such as supernovae, and the gradual shedding of materials from older stars. These particles are made up of elements like carbon, silicon, oxygen, and metals, reflecting the same basic building blocks that make up planets and life as we know it. Because cosmic dust spreads throughout galaxies and flows into interstellar space, it becomes part of a continuous cycle, enriching star-forming regions, condensing to form new stars and planets, and ultimately seeding entire solar systems with the materials necessary for life. The effect of cosmic dust on observations of the universe is significant. While space dust may seem like an inert substance, it can distort or obscure light from distant stars and galaxies, creating challenges for astronomers. When light encounters dust particles, it scatters in a phenomenon known as interstellar extinction. This scattering causes the light to shift in color, often appearing redder and dimmer than it actually is. This reddening effect can skew measurements, making it difficult to accurately gauge distances in space or study the chemical compositions of celestial bodies. Cosmic dust, therefore, acts as both a lens and a filter, reshaping the light that eventually reaches Earth-based and space-based telescopes. Advanced telescopes and instruments have been developed to counteract these distortions, yet cosmic dust remains a pervasive challenge, particularly for those studying the farthest reaches of the universe. Beyond affecting observations, cosmic dust and debris contribute significantly to the evolution of planetary bodies. Within star-forming regions, dust particles provide the material for the accretion of planets. As these particles clump together under the influence of gravity, they form larger masses that can eventually develop into planetesimals, the building blocks of planets. In fact, it is cosmic dust and other particles left over from the formation of a solar system that contribute to the creation of planets, moons, and other celestial bodies. Dust particles in protoplanetary disks, for instance, coalesce to form the embryos of planets in a process that can take millions of years, eventually leading to the formation of fully fledged planets. Thus, cosmic dust is not merely an inert background to the stars. It is a fundamental ingredient in the recipe for planets and life itself. In addition to aiding the formation of planets, space dust contributes to atmospheric development and the chemical composition of planets. When cosmic dust collides with a planet's atmosphere, it can alter the atmospheric chemistry, sometimes seeding it with organic compounds. On Earth, for example, interstellar dust delivers trace elements and minerals, which could play a role in sustaining the biosphere. Some studies suggest that cosmic dust and meteoritic particles, rich in organic molecules, may have been crucial in delivering the building blocks of life to our planet billions of years ago. Such particles are often rich in complex organic molecules, which may have helped in the prebiotic synthesis of amino acids, setting the stage for the evolution of life. While much about this process remains speculative, the hypothesis that life on Earth may have been seeded by cosmic dust lends a fascinating perspective to our origins. As dust particles travel through space, they are shaped by various forces that determine their composition, behavior, and trajectory. For example, radiation from stars exerts pressure on dust particles, known as radiation pressure, which can alter their paths. In addition, cosmic dust is influenced by magnetic fields within galaxies. Particles that are electrically charged by the ionizing radiation of nearby stars can interact with these magnetic fields, which guides their movement in complex and unpredictable patterns. This intricate ballet of forces means that dust and debris do not simply float passively but are constantly in motion, forming intricate streams and clouds that can span thousands of light years. One of the most intriguing aspects of cosmic dust is its role in creating cosmic phenomena such as nebulae. Nebulae are vast clouds of dust and gas that form some of the most beautiful and recognizable structures in space. These clouds are often regions of intense star formation, where new stars are born from the gravitational collapse of dust and gas. The dust within these nebulae scatters light, creating the colorful and ethereal glow seen in images of famous nebulae like the Orion Nebula or the Eagle Nebula. These dust-rich regions are not only visually stunning but also provide critical insights into the processes that govern star birth and death. Nebulae act as both cradles and graveyards for stars, where dust from dying stars mingles with the material that will eventually form new ones, underscoring the continuous cycle of cosmic creation and destruction. Space debris, while often overshadowed by cosmic dust, also plays a significant role in the story of the universe. Unlike cosmic dust, which is distributed widely across the universe, space debris is concentrated within specific areas, such as the asteroid belt in our solar system. This debris includes remnants from the formation of planets and moons, as well as fragments from collisions between larger objects. Over millions of years, these fragments can either coalesce into new bodies or remain as scattered particles, orbiting the Sun in paths that occasionally intersect with those of planets. When space debris enters a planet's atmosphere, it creates a fiery display known as a meteor shower. These events, while fleeting, provide direct evidence of the presence of cosmic debris and highlight the interconnected nature of planetary systems. The constant influx of cosmic debris impacts the surfaces of planets and moons, especially those without protective atmospheres. On Earth, most small meteoroids burn up upon entry due to atmospheric friction, but planets and moons without atmospheres, such as Mercury or our Moon, experience frequent impacts from cosmic debris. These impacts shape their surfaces over time, creating craters and ejecta that alter the landscape. Through a process called impact gardening, repeated collisions can mix and churn the surface layers, redistributing materials and exposing new layers to the vacuum of space. The scars left by cosmic debris serve as a historical record, providing clues to the history and evolution of these celestial bodies. By studying impact sites, scientists can gain insights into the age and composition of planetary surfaces, which helps reconstruct the history of our solar system. In recent years, scientists have also begun to consider the role of cosmic dust and debris in the climate of planets. On Earth, for example, cosmic dust particles that reach the upper atmosphere can interact with atmospheric chemicals and potentially influence weather patterns. These particles act as nuclei for cloud formation, and though their impact on global climate is still under study, some researchers propose that cosmic dust may contribute to long-term climate cycles. During periods of increased meteoritic activity, such as when Earth passes through dense clouds of debris, the influx of particles could theoretically lead to slight changes in atmospheric dynamics. While this effect is subtle compared to factors like greenhouse gases or volcanic activity, it represents yet another way that cosmic dust quietly shapes our world. The study of cosmic dust has expanded dramatically with the advent of advanced space missions and technology. Space agencies like NASA and ESA have launched missions specifically aimed at collecting and analyzing dust particles from space. The Stardust mission, for instance, was the first to return samples of dust from a comet, giving scientists a direct look at the materials that compose these ancient cosmic wanderers. These missions reveal details about the composition of dust and provide new insights into the processes that govern the formation and evolution of our solar system. Analyzing samples of cosmic dust allows researchers to test hypotheses about the chemical makeup of the early solar system and the role of interstellar material in shaping our planetary neighborhood. The implications of cosmic dust research extend beyond our solar system to the study of exoplanets and the potential for life beyond Earth. Dusty disks observed around young stars and distant star systems often signal the presence of planet formation. These disks are similar to the protoplanetary disk that surrounded our Sun during its infancy, from which the planets of our solar system eventually formed. By studying these distant dusty environments, scientists can observe planet formation in real time, capturing snapshots of processes that occurred billions of years ago in our own solar system. This research could one day answer questions about how common planetary systems like ours are in the galaxy, and what conditions might support life elsewhere. As we continue to explore the universe, cosmic dust and debris challenge our understanding of what makes life possible. The idea that life on Earth may have been partially seeded by materials originating from distant stars invites us to consider our connection to the cosmos in a profound way. The mystery of how life began intertwines with the journey of dust particles that have traveled through interstellar space, survived the fiery plunge through Earth's atmosphere, and possibly contributed to the very molecules that make up our DNA. This cosmic perspective redefines our sense of belonging in the universe, suggesting that we may, in a way, be descendants of the stars. Cosmic dust and debris thus serve as a reminder of our shared origins with the cosmos, blurring the lines between life on Earth and the processes that shape the universe itself. As astronomers observe distant galaxies, they frequently encounter massive clouds of cosmic dust that, in many ways, act as interstellar time capsules. These dust clouds contain elements forged in the hearts of stars and carry remnants of cosmic events that occurred billions of years ago. By analyzing the light that passes through these dust clouds, scientists can decode their composition, uncovering the presence of elements like hydrogen, helium, carbon, and even complex organic molecules. These molecules are critical because they provide a foundation for life as we understand it. Some of the organic compounds detected in space dust include polycyclic aromatic hydrocarbons, PAHs, which are among the most complex molecules found in space and may play a role in the development of life. The sheer size of some interstellar dust clouds, often spanning thousands of light-years, means that they impact large regions of space. These clouds absorb and re-emit energy, sometimes generating heat that affects the star systems within them. This energy interaction creates feedback loops that can either stimulate or hinder star formation in certain regions. For example, as a young star forms, it can generate intense radiation that clears out nearby dust, halting the creation of additional stars in its immediate vicinity. Conversely, in other regions, the pressure exerted by massive dust clouds can compress gas into dense regions that ignite new star formation. Thus, cosmic dust not only contributes to star birth but also influences the growth and structure of entire galaxies, helping to shape the architecture of the universe. The impact of cosmic debris on planetary systems is especially evident when examining the asteroid and Kuiper belts within our solar system. These regions are populated with remnants from the solar system's early days, and the objects within them occasionally interact with each other, resulting in collisions that produce smaller fragments. When these fragments are ejected from the belts, they can be pulled by gravitational forces toward the inner planets, including Earth. Many of these objects enter our atmosphere as meteoroids, creating meteors or shooting stars, when they burn up due to friction. Larger fragments that survive the descent impact the surface, becoming meteorites, and provide scientists with valuable material to study the early solar system's composition. The asteroid belt, located between Mars and Jupiter, contains a mixture of rocky and metallic objects that provide a fascinating glimpse into the materials that did not coalesce into planets. These asteroids are relics from the formation of our solar system and vary in size from tiny particles to objects hundreds of kilometers across. Over time, the gravitational influence of Jupiter has prevented these fragments from clumping together into a single planetary body. The Kuiper belt, found beyond Neptune, holds icy bodies and is home to dwarf planets like Pluto. This belt represents a colder, more distant region of cosmic debris, and scientists believe it holds clues to the formation of the outer solar system and the conditions present in the distant past. The dynamic nature of cosmic debris becomes evident when considering the potential hazards it poses to planetary systems. Objects from both the asteroid and Kuiper belts have the potential to collide with planets, creating massive impacts that can alter climates, surface features, and even the course of evolution. For example, it is widely believed that a massive asteroid impact contributed to the extinction of the dinosaurs on Earth around 66 million years ago. Events like these are rare but demonstrate the significant role that cosmic debris can play in shaping the histories of planets. Understanding the behavior of these objects and their impact probabilities is crucial for planetary defense and for protecting Earth from potential collisions in the future. As scientists uncover more about the role of cosmic dust in galaxy formation and evolution, they also face intriguing questions about the origins of these particles and their movement across vast distances. Some dust particles are remnants of the Big Bang, the universe's initial explosion, while others are continuously created in regions of intense star formation and destruction. These particles travel through interstellar space, occasionally collecting around the gravitational wells of stars or planets. As they move, they accumulate new materials and undergo transformations, adding layers of complexity to their composition. When these particles come together in sufficient densities, they may form vast interstellar clouds, providing fertile environments for future star formation. One of the mysterious phenomena associated with cosmic dust is the Zodiacal light, a faint glow visible in the night sky. This phenomenon occurs when sunlight scatters off dust particles within the plane of the solar system, creating a soft light that is sometimes visible before dawn or after dusk. The zodiacal light reveals the presence of dust in our solar system and hints at the ongoing process of dust accretion, interaction with sunlight, and its gradual dispersal. Scientists studying this light can glean insights into the distribution of dust within the solar system and how it may influence the long-term stability of planetary orbits. Recent advances in technology allow astronomers to study cosmic dust with unprecedented precision. Infrared telescopes, in particular, are invaluable for observing dust clouds that are otherwise invisible in optical wavelengths. Since cosmic dust emits most of its energy in the infrared spectrum, telescopes like the James Webb Space Telescope provide detailed views of these clouds, revealing their composition and structure. This information not only enriches our understanding of cosmic dust but also enhances our knowledge of galaxy formation, the birth of stars, and the potential for habitable planets around distant stars. Moreover, as scientists look toward future space missions, the study of cosmic dust is gaining new momentum. Proposed missions aim to collect and return samples of interstellar dust, providing a direct link to materials from beyond our solar system. These samples could revolutionize our understanding of the chemical processes that occur in the interstellar medium and reveal new details about the conditions that foster planet formation. In parallel, proposed missions to the Kuiper belt and beyond seek to analyze objects in these regions up close, offering insights into the origins of the solar system's cold outer regions. As we continue to probe the mysteries of cosmic dust and debris, the field of astrobiology also stands to benefit. The notion that cosmic dust may carry organic molecules or even primitive microbial life forms raises profound questions about the potential for life to exist elsewhere in the universe. Some researchers hypothesize that space dust could act as a carrier for life, dispersing organic compounds or microbial spores across interstellar distances in a process called Panspermia. This idea, while speculative, suggests that life on Earth may be part of a larger, interconnected web of life that spans the cosmos. If future missions detect organic compounds or signs of microbial life in cosmic dust, it could provide compelling evidence that life is not unique to Earth. The impact of cosmic dust extends even to the outer reaches of our solar system, where it encounters the heliosphere, a vast bubble created by the solar wind, which shields the inner solar system from interstellar dust and cosmic rays. The heliosphere acts as a boundary, protecting planets like Earth from harmful radiation while still allowing small amounts of interstellar dust to enter. Studying how cosmic dust interacts with the heliosphere provides insights into the structure of our solar system and the role of stellar winds in shaping cosmic environments. In a broader sense, the study of cosmic dust and debris challenges our understanding of the universe's scale and complexity. These particles, though small, offer clues to some of the most profound questions in science. How did our solar system form? What materials are necessary to support life? And how does cosmic matter cycle throughout the galaxy? As new technologies emerge and our ability to study the cosmos improves, the mysteries surrounding cosmic dust and debris continue to captivate scientists and the public alike, revealing layers of complexity in a universe that seems endless in both its size and its potential for discovery. From the earliest stars that seeded the universe with elements, to the distant galaxies veiled in dust, cosmic dust and debris remind us that even the tiniest particles have a role to play in the grand design of the cosmos. Each particle, each fragment, carries a story, a history of the universe encoded within its atomic structure. And as we reach further into space, gathering data from dust clouds, meteors, and interstellar matter, we begin to uncover the secrets of our own origins, tracing our existence back to the first atoms forged in the fires of ancient stars. Cosmic dust and debris not only serve as physical remnants of stellar events but also as messengers from other star systems, giving us glimpses into distant worlds and phenomena beyond our reach. These tiny particles, traveling across immense cosmic distances, bear the imprints of their birthplace, sometimes in regions so far away that direct observation would be nearly impossible. Through spectroscopy, scientists can analyze the light that passes through cosmic dust and extract details about its elemental composition, temperature, and movement. This level of analysis enables researchers to discern the specific origins of dust particles, determining whether they emerged from a supernova explosion, a dying star shedding its outer layers, or an early solar nebula. Cosmic dust often forms in places where intense astrophysical processes occur, such as supernovae and planetary nebulae. During a supernova, the intense pressure and temperature drive fusion processes that create heavier elements, which are then expelled into space along with lighter elements. As this material spreads across the galaxy, it cools and condenses into fine dust particles. These particles, enriched with elements like carbon, silicon, iron, and oxygen, become the raw materials for new stars, planets, and even the molecules essential to life. Each particle is like a fossil of its cosmic journey, carrying with it the history of stars that lived and died, long before our own sun existed. The interstellar medium, filled with dust and gas, is a constantly evolving environment where particles interact, collide, and transform. When dust grains collide in this medium, they can either shatter into smaller fragments, or, under the right conditions, clump together, forming larger aggregates. These aggregates may eventually grow massive enough to attract more material, acting as the building blocks for planets. This process, known as accretion, is central to the formation of planetary systems. It demonstrates how even the smallest fragments of dust can set off chain reactions that culminate in the creation of complex structures like planets and moons. Interestingly, the physical properties of cosmic dust particles can also influence the colors and characteristics of the light we observe. When light encounters dust, shorter wavelengths, such as blue, are scattered more than longer wavelengths, giving rise to phenomena like reddening. This effect is observable when we look at stars through regions dense with dust, causing them to appear redder than they are. This reddening effect, while a hindrance to direct observations, also allows astronomers to gauge the amount and distribution of dust in a given area, making cosmic dust both an obstacle and a tool in the study of the universe. In certain cases, cosmic dust clouds are dense enough to completely obscure light, blocking our view of the stars behind them. These dark nebulae, regions of space where dust and gas are so thick that they absorb visible light, serve as cosmic nurseries where new stars are born. Within these clouds, gravitational forces pull gas and dust inward, creating dense regions that eventually collapse to form stars. This cycle of birth and destruction, driven in part by cosmic dust, is a fundamental process in galaxy evolution. As stars form and die, they release dust back into space, perpetuating the cycle and ensuring that the universe remains a dynamic, ever-changing environment. Dust plays a particularly intriguing role in shaping planetary systems, as it is instrumental in both the early and late stages of planet formation. In the early stages, dust particles collide and stick together, forming pebbles, boulders, and eventually planetesimals, the building blocks of planets. Over millions of years, these planetesimals coalesce into protoplanets, which eventually form into planets. Dust disks around young stars, known as protoplanetary disks, are the nurseries where this process takes place. These disks contain a diverse array of particles, from tiny silicate grains to icy fragments, providing the raw materials for rocky planets, gas giants, and icy worlds. As the planets form, their gravitational influence begins to clear out nearby debris, sculpting gaps and rings within the disk. This interaction between planets and dust shapes the architecture of the developing planetary system, determining the size, composition, and arrangement of planets and other celestial bodies. Observations of protoplanetary disks around other stars have revealed intricate structures, including gaps, spirals, and rings that suggest the presence of forming planets. By studying these disks, astronomers can better understand the mechanisms that shaped our own solar system, offering clues about the conditions that may lead to habitable planets around distant stars. In addition to its role in planet formation, cosmic dust continues to interact with planetary systems long after they have formed. Dust from comets and asteroids constantly enters Earth's atmosphere, producing meteors as it burns up upon entry. Occasionally, larger fragments survive this fiery descent and reach the ground as meteorites. These pieces of space debris provide valuable samples that scientists can study, revealing the chemical makeup and history of objects from the far reaches of the solar system. By analyzing isotopes within these meteorites, researchers gain insights into the age and origin of the solar system, unlocking stories that stretch back billions of years. Cosmic dust has a profound impact on our atmosphere and environment, too. When high-altitude dust from meteors and other sources accumulates, it can reflect sunlight, affecting the climate. This dust can create noctilucent clouds, thin, bright clouds visible only during twilight, at the edge of Earth's atmosphere. These clouds are a reminder of the continuous exchange between Earth and space, as particles from the cosmos blend with our atmosphere in subtle but significant ways. Furthermore, cosmic dust plays a role in protecting Earth from harmful solar and cosmic radiation. Dust particles in space act as a buffer, absorbing some of the energy from cosmic rays before they reach the planet. In the absence of Earth's atmosphere, space dust in the solar system contributes to the formation of a protective layer around our planet. The heliosphere, a vast bubble formed by the solar wind, shields the inner solar system from a significant portion of interstellar dust and cosmic rays, creating a relatively stable environment for life on Earth to thrive. This cosmic shield is a reminder of the delicate balance that exists between the Earth and the vast forces at play within the galaxy. As scientists probe deeper into the mysteries of cosmic dust, they encounter fascinating evidence that suggests this material may play a role in the distribution of organic compounds across the universe. Organic molecules, such as amino acids and simple sugars, have been detected within cosmic dust, leading to the theory that these building blocks of life may be distributed throughout the cosmos by dust particles. The presence of such compounds in meteorites that have fallen to Earth supports the idea that the ingredients for life are not unique to our planet but may be common throughout the galaxy. The potential for cosmic dust to carry organic molecules raises the intriguing possibility that life on Earth could have been seeded by material from outer space, a concept known as Panspermia. According to this theory, microscopic life forms or the precursors of life could have traveled across space within dust particles, surviving the harsh conditions of interstellar travel before reaching Earth or another habitable planet. While panspermia remains speculative, the discovery of organic compounds in cosmic dust strengthens the argument that life may exist elsewhere in the universe, connected by the vast network of dust and debris that permeates space. In a broader sense, the study of cosmic dust challenges our understanding of what it means to be alive and the boundaries of biological material. If life's building blocks are indeed spread across the universe within cosmic dust, it may redefine our search for extraterrestrial life, encouraging scientists to look beyond planets and moons and consider the potential of dust clouds, comets, and asteroids as carriers of life's seeds. This shift in perspective could open new frontiers in astrobiology, pushing the boundaries of our exploration to encompass the very particles that fill the spaces between stars. Our growing knowledge of cosmic dust also has practical implications for future space exploration. Dust particles, while small, can pose significant risks to spacecraft traveling through space. High-speed collisions with dust particles can damage spacecraft surfaces, disrupt instruments, and even penetrate protective shielding. To mitigate these risks, engineers are developing advanced materials and techniques to shield spacecraft from dust impacts, ensuring the safety of future missions to explore the farthest reaches of our solar system and beyond. Moreover, understanding the properties of cosmic dust is essential for designing instruments that can accurately observe distant objects. Dust can interfere with observations by scattering and absorbing light, a challenge that astronomers must overcome when studying faint or distant celestial bodies. Innovations in telescope technology, such as adaptive optics and infrared imaging, are helping scientists see through dust and capture clear images of objects obscured by these particles. These advancements not only enhance our understanding of cosmic dust but also allow us to peer deeper into the universe, uncovering details about galaxies, nebulae, and star-forming regions. As we continue to explore the cosmos, cosmic dust serves as both a challenge and an ally, a source of information and a reminder of the complexity of the universe. Each particle, though seemingly insignificant, contributes to the grand narrative of cosmic evolution, carrying within it the history of stars, planets, and even life itself. In studying cosmic dust, we are not only learning about the universe but also discovering the origins of our own existence, tracing the threads that connect us to the stars. As we gaze into the vast expanse of space, cosmic dust and debris remind us that the universe is far from empty. It is filled with the remnants of stellar births and deaths, particles that have traveled across galaxies, and possibly the ingredients for life itself. The mysteries of cosmic dust and debris are a testament to the interconnectedness of all things, a cosmic dance that binds together planets, stars, and life in ways we are only beginning to understand. The study of cosmic dust and debris is, in many ways, a journey back in time, a way to witness the early moments of the universe, to understand the processes that gave rise to stars, planets, and ultimately, life. Each discovery brings us closer to answering the fundamental questions of our existence. Where did we come from? Are we alone? This intricate and invisible dance of cosmic dust and debris, spanning billions of years, holds profound implications for the future of space exploration and for our understanding of the universe's beginnings. Each particle of dust acts as a testament to the countless cosmic processes that shape the universe as we know it, a universe that continues to evolve and grow, with dust as one of its primary building blocks. One of the most compelling aspects of cosmic dust is its role in tracing the formation and movement of stars, galaxies, and planetary systems. Dust particles are far from passive. They interact dynamically with the forces at play in the universe, responding to gravity, magnetic fields, and the radiation from nearby stars. When radiation from a young, energetic star hits dust particles, it creates a pressure known as radiation pressure. This force can push dust particles away from the star, forming structures such as dust tails on comets, and even influencing the shapes of nebulae and dust clouds. Such forces are responsible for the unique, often stunningly beautiful patterns that we observe in space, from the sweeping arcs of spiral galaxies to the intricate, wavy structures of gas and dust in nebulae. Moreover, the radiation from stars can actually change the physical and chemical properties of dust particles. Intense ultraviolet radiation, for instance, can alter the composition of cosmic dust by breaking molecular bonds or ionizing atoms, thereby creating complex molecules or even initiating chemical reactions. This phenomenon suggests that cosmic dust could act as a catalyst for chemical evolution on an interstellar scale. Over millions of years, dust particles in dense molecular clouds could undergo transformations, forming increasingly complex molecules that resemble organic compounds, the building blocks of life. In fact, astronomers have detected complex organic molecules within interstellar dust clouds, a discovery that has significant implications for the origins of life. This observation lends support to the theory that cosmic dust may play a fundamental role in distributing life's precursors across the galaxy, possibly planting the seeds of biology on otherwise barren planets. If cosmic dust carries such compounds through space, it raises the tantalizing possibility that life could be a cosmic phenomenon, not confined to Earth but potentially seeded throughout the universe by these tiny messengers of organic material. The distribution of cosmic dust is not uniform across the galaxy. Rather, it is often concentrated in certain regions where stars are born and die. These regions, known as stellar nurseries, are bustling with dust, gas, and intense activity. Within these regions, gravitational forces pull together dust and gas, sparking the formation of new stars. As stars evolve, they continue to interact with the surrounding dust, shaping it and eventually contributing to it once again. When a massive star reaches the end of its life in a supernova explosion, it releases vast amounts of dust and debris, dispersing elements like carbon, oxygen, and silicon, materials crucial for life, throughout the surrounding space. Thus, cosmic dust serves as both the birthplace and the legacy of stars, marking the cyclical nature of cosmic evolution. In addition to being essential to stellar life cycles, cosmic dust affects the light we observe from distant stars and galaxies, influencing our understanding of the universe's structure and composition. When light from distant objects passes through regions dense with dust, it becomes dimmed and reddened in a process known as interstellar extinction. This effect complicates astronomical observations, as dust can obscure and alter the appearance of celestial bodies, making them appear dimmer or redder than they actually are. However, astronomers have developed methods to correct for this effect, using the properties of dust to estimate its amount and distribution across space. By understanding interstellar extinction, scientists can more accurately measure the distances and luminosities of faraway stars and galaxies, refining our map of the universe. Even in our own solar system, cosmic dust has a marked impact. The zodiacal light, a faint, triangular glow seen in the night sky just after sunset or before sunrise, is caused by sunlight scattering off interplanetary dust within the plane of our solar system. This dust, largely left over from the formation of planets and the gradual erosion of comets and asteroids, continues to drift through space, orbiting the Sun and interacting with planets. It acts as a faint reminder of our solar system's origins, an ever-present sign of the dusty chaos from which planets were born. Our solar system is a dynamic place, with cosmic dust constantly being replenished as comets approach the Sun and release material, and as asteroids collide and fragment. This ongoing supply of dust plays a subtle yet continuous role in shaping the environment of planets, including Earth. For instance, micrometeorites, tiny particles of cosmic dust, regularly fall to Earth, adding tons of extraterrestrial material to the planet each year. Though small, these particles can carry with them complex organic molecules, hinting that cosmic dust may have delivered some of the precursors to life on our own planet billions of years ago. The continuous arrival of micrometeorites also serves as a reminder of our connection to the broader cosmos, as these particles have traveled vast distances before finally settling on Earth. Beyond their impact on individual planets, dust particles also interact with entire planetary systems. Dust disks around young stars, for example, can shape the orbits and compositions of forming planets. In cases where a massive planet orbits within a dust disk, its gravitational pull can carve out gaps and rings, influencing the distribution of material around the star. These interactions may lead to the formation of planetary rings or even guide the development of secondary, smaller planets. Observations of such disks around other stars give us a window into the early stages of planet formation, shedding light on the processes that created our own solar system. In fact, the study of cosmic dust and debris around other stars has revealed some of the most mysterious phenomena in modern astronomy. Around some stars, particularly those nearing the end of their life cycles, scientists have detected unexpected structures within dust disks, including complex spiral patterns, clumps, and arcs. These structures hint at the presence of unseen forces or objects, possibly hidden planets, binary companions, or even massive clouds of gas, that influence the dust distribution in ways that are still poorly understood. Such findings highlight the intricate and sometimes perplexing interactions that take place in dust-rich environments, illustrating that dust is far from a passive substance, but is actively shaped by the dynamics of the systems it inhabits. The behavior of cosmic dust can even reveal hidden celestial bodies that would otherwise be invisible to us. For example, dark dust clouds can obscure stars, planets, and other objects behind them, creating mysterious shadows in our observations. By carefully studying these shadows and analyzing the movement of dust within them, astronomers can infer the presence of hidden objects, including rogue planets that wander the galaxy without orbiting any star. In this way, dust acts as both an obscurer and a revealer, hiding some aspects of the universe while offering clues to others. Even in the vastness of intergalactic space, cosmic dust is present, albeit in lower densities than within galaxies. This intergalactic dust may seem insignificant, but it has a profound effect on our understanding of the cosmos. When light from distant galaxies travels through intergalactic dust, it becomes faintly reddened and dimmed, an effect that must be accounted for in cosmological studies. This intergalactic dust subtly skews our observations of the distant universe, affecting measurements related to the expansion rate of the universe and the nature of dark energy. Thus, even the smallest particles of dust can impact some of the biggest questions in cosmology. As our understanding of cosmic dust deepens, so does our awareness of the challenges it presents to space exploration. Dust particles, particularly in regions dense with debris, pose significant risks to spacecraft. Traveling at high speeds, even the smallest dust particles can puncture or erode spacecraft surfaces, causing potential damage to critical systems. Missions to outer planets, moons, and distant asteroids must contend with these particles, designing protective measures and anticipating dust-related hazards. In recent years, engineers have explored innovative solutions, such as dust-resistant coatings and shielded designs, to safeguard future missions, enabling humanity to explore increasingly distant and dust-filled regions of space. From an engineering standpoint, studying cosmic dust is not merely about mitigating its effects but also about harnessing its potential as a resource. On planets and moons, dust particles, composed of elements like silicon, iron, and carbon, could serve as raw materials for constructing habitats, life support systems, and equipment in extraterrestrial environments. In this way, cosmic dust is seen not just as a scientific subject but also as a potential enabler of long-term human presence in space, helping to create a self-sustaining future among the stars. Ultimately, cosmic dust and debris reveal much about the universe's complexity, and yet they are reminders of its interconnectedness. From the microscopic scales of interstellar particles to the macroscopic interactions that shape planetary systems, dust connects all cosmic objects, forming a continuum of material that stretches across galaxies and billions of years. Dust particles, though small, hold within them the stories of stars, the birth of planets, and the spread of life's building blocks, a cosmic tapestry woven from the remnants of countless stellar generations. As we continue to probe the mysteries of cosmic dust, each discovery brings us closer to understanding our origins and place in the universe. Dust serves as a bridge between the known and the unknown, the seen and the unseen, giving us a tangible connection to the vast and often incomprehensible cosmos that surrounds us. With every advancement in telescope technology, every new space mission, and every piece of data analyzed, we peel back another layer of the mysteries that dust holds, unraveling the secrets of the stars, the galaxies, and perhaps the origins of life itself. In this endless quest for knowledge, cosmic dust remains a humble but profound reminder that even the smallest particles hold the potential to unlock the deepest mysteries of existence. As we venture deeper into the study of cosmic dust, its profound influence on the processes that shape the universe becomes increasingly evident. The nature of cosmic dust is far from simple, as each tiny particle carries a complex history of interactions, transformations, and compositions that reveal essential details about the environments from which they originate. This cosmic dust, drifting through space, is made up of an array of materials, from silicates and carbonaceous compounds to complex organic molecules, each contributing unique properties to the medium in which it exists. These particles provide an extensive record of stellar processes, galactic dynamics, and even chemical evolution, making them critical to understanding how the universe as we know it came to be. The origins of cosmic dust are as varied as its composition. Some dust forms in the cooling envelopes of red giant stars, as they release gas and material into space in the later stages of their lives. Other dust particles emerge from supernova explosions, where massive stars end their lives in spectacular bursts, ejecting vast quantities of material into space. This stellar material undergoes rapid cooling as it travels through space, allowing atoms to combine into molecules and then condense into solid particles of dust. This cycle of creation and destruction is continuous, as dust particles survive for millions of years, until they eventually collide, fragment, or are incorporated into larger structures, such as asteroids, comets, or even new stars and planets. This continual recycling of dust is part of what makes it so fascinating. Dust does not simply float through space in isolation. Rather, it moves through different regions, interacts with other materials, and even carries with it signatures of its origins. For example, dust grains formed in the intense heat of a supernova explosion have isotopic signatures distinct from those formed in the cooler envelopes of red giants. These differences allow scientists to trace individual dust grains back to specific types of stars or even to particular events, giving us a snapshot of the cosmic conditions at the time of their formation. One of the intriguing challenges in studying cosmic dust is how it shapes and obscures our observations of the universe. Dust particles are typically only a few micrometers across, smaller than a single human cell, yet their presence can significantly affect the light that passes through them. When starlight encounters a dust cloud, it scatters and absorbs certain wavelengths of light, altering the star's appearance. This process, known as interstellar extinction, makes distant stars and galaxies appear dimmer and redder, complicating efforts to measure their true distances and properties. Without accounting for the effects of dust, astronomers would have a distorted view of the cosmos, misinterpreting the size, structure, and evolution of the universe. The impact of cosmic dust on astronomical observations extends beyond simple dimming. Dust clouds can also produce beautiful, ethereal phenomena when they reflect and scatter light. One of the most visually striking examples of this effect is the appearance of reflection nebulae, clouds of dust illuminated by nearby stars, creating a soft, ghostly glow. In these nebulae, the dust particles scatter blue light more effectively than red light, giving the nebulae their characteristic blue hue. This scattering effect is similar to the way Earth's atmosphere makes the sky appear blue during the day. Reflection nebulae thus offer a direct view of how dust interacts with starlight, creating some of the most iconic and photogenic sights in the night sky. While reflection nebulae are stunning, they are only one type of structure that cosmic dust can form. In regions where dust is dense, it can block out starlight almost entirely, creating dark nebulae or Bach globules, compact, cold clouds that appear as black patches against the starry background. These dense dust clouds are fascinating because they serve as the nurseries of new stars. Within the cores of these dark nebulae, gas and dust are pulled together by gravity, gradually collapsing until the pressure and temperature are high enough to ignite nuclear fusion, giving birth to a new star. Dust, therefore, plays a dual role. It both hides and enables the formation of stars, contributing to the cycle of creation in the galaxy. The role of cosmic dust in planet formation is equally profound. In the protoplanetary disks that surround young stars, dust particles collide and stick together, forming larger and larger clumps that eventually become the building blocks of planets. These dusty disks are the early stages of planetary systems, where dust grains, enriched by elements like carbon, oxygen, and silicon, start to form pebbles, boulders, and eventually planetary cores. Observations of these disks around other stars have shown a range of fascinating structures, including rings, gaps, and spiral arms, which may indicate the presence of forming planets that are shaping the distribution of dust and gas in their orbits. In this way, cosmic dust not only reveals itself in striking patterns but also marks the locations where new worlds are coming into existence. In addition to acting as the seeds of planet formation, dust particles in protoplanetary disks can affect the chemical environment of young planetary systems. Within these disks, radiation from the central star can cause chemical reactions on the surfaces of dust grains, producing complex organic molecules. This process, known as surface chemistry, is a potential pathway for the synthesis of prebiotic compounds, molecules that are the precursors to life. Observations of protoplanetary disks have revealed the presence of molecules like formaldehyde, methanol, and even amino acids, suggesting that the building blocks of life might be widespread in the universe. If these organic molecules can survive the planet-forming process, they may become incorporated into newly formed planets, setting the stage for the development of life. The ability of dust to form and transport organic compounds has implications for astrobiology and the search for life beyond Earth. If cosmic dust carries complex organic molecules throughout space, it raises the possibility that these molecules could be delivered to young planets via dust particles, comets, or meteorites. On Earth, for example, scientists have found organic compounds within meteorites that likely formed in the early solar system, indicating that such compounds could have been available to our planet as it was forming. This idea, known as Panspermia, suggests that life's building blocks, or even life itself, might travel between planets and star systems on dust particles and debris. If true, Panspermia would mean that cosmic dust plays a central role in spreading life's ingredients across the galaxy. The concept of cosmic dust as a carrier of life's building blocks also opens questions about whether life might be more common in the universe than we currently believe. The discovery of organic molecules in interstellar clouds and protoplanetary disks has expanded our understanding of where these molecules can form, demonstrating that the conditions necessary for complex chemistry exist far beyond our solar system. As we continue to explore and analyze cosmic dust, we may find even more evidence that organic compounds are widespread, hinting at the possibility of life in places we have yet to imagine. In terms of scientific exploration, cosmic dust has become a significant focus for space missions seeking to understand the fundamental processes of the cosmos. The Stardust mission, launched by NASA, is a prime example of humanity's attempt to capture and analyze cosmic dust. Stardust was designed to collect particles from the coma of a comet and from interstellar dust passing through our solar system. The samples returned to Earth provided invaluable information about the composition and structure of dust particles from beyond our solar system, revealing new insights into the early solar system's materials. This mission marked one of the first times that scientists were able to study interstellar dust particles directly, providing a wealth of data about their structure and composition. The collection and study of cosmic dust samples on Earth have revealed intricate structures within individual particles, showing that they contain a variety of minerals and organic compounds. These particles are like tiny time capsules, preserving evidence of the physical and chemical processes they have undergone over millions or even billions of years. By examining their composition, scientists can trace the origins of dust particles back to specific types of stars or regions of space, reconstructing the history of the matter that makes up the universe. Cosmic dust and debris have implications not only for our understanding of the past but also for future space exploration. Dust is a persistent challenge for spacecraft, particularly in the vicinity of planets with thin or no atmospheres, where dust particles are not shielded or filtered. On the Moon, for example, lunar dust is notoriously abrasive and clings to surfaces due to its electrostatic properties, posing a risk to equipment and astronauts. Future missions to the Moon and Mars will need to address these challenges, developing new technologies to protect against dust and ensure the safety of explorers and equipment. This dust, though seemingly simple, is a formidable obstacle that scientists and engineers must account for in every phase of mission planning. The significance of cosmic dust extends beyond its physical effects. It also challenges us to rethink how we define the boundaries of planets, stars, and even galaxies. Dust clouds fill the spaces between stars, creating what is known as the interstellar medium, a vast, dynamic region that connects stellar systems and affects the transmission of energy and matter across the galaxy. This medium is not empty but teeming with particles that interact, collide, and merge, creating a vast network of material that links all parts of the galaxy. Dust and gas within the interstellar medium act as a kind of galactic ecosystem, where energy is exchanged, elements are recycled, and new stars and planets are born. Ultimately, Cosmic dust and debris embody the cycle of cosmic evolution, a cycle that includes the formation of stars, the birth of planets, and the distribution of life's building blocks across space. Each dust particle is a fragment of the cosmic narrative, a piece of the vast puzzle that makes up the universe. The study of these tiny particles has reshaped our understanding of the cosmos, revealing connections between stars, planets, and life itself. Cosmic dust may be small, but it holds within it the secrets of creation, transformation, and interconnectedness, reminding us of our place in a universe that is both vast and deeply interwoven. Each particle of cosmic dust is not merely a silent traveler but a storyteller, holding within it the history of its cosmic journey across eons. These tiny, nearly invisible particles tell us about the life cycles of stars, the formation of planets, and even the potential origins of life itself, underscoring the profound relationship between dust and the grand processes that govern the universe. As we peer deeper into the vastness of space, the significance of dust becomes even more apparent in shaping the architecture of galaxies and the dynamics of star formation. In dense, cold regions of galaxies known as molecular clouds, dust grains provide surfaces upon which hydrogen atoms can meet, bond, and form molecular hydrogen, a crucial step in creating the conditions necessary for star birth. These clouds, laden with dust, collapse under their own gravity to form new stars, while simultaneously being shaped and sculpted by powerful feedback from young, hot stars. This interaction between dust and starlight not only governs the formation of new stars but also dictates the ultimate fate of the molecular clouds themselves, as intense radiation and stellar winds erode and disperse them over time. Dust's role in galaxies extends beyond the molecular clouds, as it fills the spaces between stars in a diffuse manner, absorbing and re-emitting energy across various wavelengths. This emission in infrared and submillimeter wavelengths allows astronomers to map the distribution and density of dust across galaxies, even in regions hidden from optical telescopes. This ability to track dust reveals otherwise invisible structures within galaxies, such as spirals, filaments, and rings, providing insight into the processes that influence galactic evolution. By tracing the movement and concentration of dust, astronomers can uncover patterns of star formation and even identify regions rich in raw materials for future stellar nurseries. One of the profound impacts of cosmic dust on our view of the universe is its contribution to phenomena known as cosmic extinction and reddening. As light from distant stars and galaxies passes through dust clouds, it gets scattered and absorbed, especially at shorter wavelengths, leading to a reddening of the observed light. This reddening effect, akin to watching a sunset through a dusty haze, creates an optical illusion that makes stars appear redder and dimmer than they truly are. Such distortions can affect our understanding of the age, distance, and intrinsic brightness of celestial objects, highlighting the need for careful correction methods and astronomical observations. Without accounting for the influence of dust, we would significantly misinterpret the properties of many cosmic objects, making it essential for astronomers to factor in dust's impact to get a clearer picture of the universe. Dust also serves as a protective shield in space, creating cocoons around forming stars and planetary bodies. These cocoons of dust and gas shield young stars from intense radiation, enabling the stars to reach a stable phase of nuclear fusion. In planetary systems, dust can protect early atmospheres and surfaces from cosmic radiation, which might otherwise strip away delicate compounds crucial for the development of life. On Earth, the dust that continually settles from space acts as a constant reminder of our planet's connection to the cosmos. This cosmic rain includes particles from interstellar dust clouds, cometary debris, and asteroid fragments, contributing material to our planet from beyond our solar system. These dust particles, when analyzed, reveal isotopic signatures and elemental compositions that hint at their origins, allowing scientists to piece together the broader cosmic landscape from which they came. Even on a galactic scale, dust has an essential role in shaping the fate of entire galaxies. Dust and gas cycles are among the key processes in galaxies, as supernova explosions and stellar winds enrich the interstellar medium with elements heavier than hydrogen and helium, elements essential for the formation of planets and life. These processes create feedback loops where the energy released by dying stars injects momentum into the surrounding gas, dispersing dust and gas that may eventually cool and condense into new stars and planets. This cyclical exchange of dust and gas is not just an incidental process, it is a fundamental mechanism that maintains the life cycle of galaxies, enriching them with the materials needed to spawn future generations of stars and potentially habitable planets. Our understanding of cosmic dust has transformed in recent years thanks to advancements in observational technology. Instruments like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided astronomers with unprecedented resolution and sensitivity, enabling the study of dust particles and molecular clouds in distant galaxies and even across cosmic time. With these tools, astronomers have mapped intricate dust structures, observed the formation of dust-rich galaxies, and even detected dust in the early universe, just a billion years after the Big Bang. These observations have revealed that dust is present even in the early stages of galaxy formation, playing a critical role in shaping the first galaxies and possibly influencing the rate of star formation in the young universe. One of the most intriguing aspects of cosmic dust is the role it might play in shielding young planetary systems from harmful radiation, potentially aiding in the formation of habitable environments. As young stars undergo rapid fluctuations in radiation output, dust clouds and protoplanetary disks may absorb and block some of this harmful radiation, creating more stable conditions for planets forming within these disks. This protective effect might allow complex organic molecules to survive and persist on young planets, increasing the likelihood that life-supporting conditions could eventually arise. By shielding planets from intense radiation, cosmic dust may indirectly facilitate the emergence of life, underscoring its importance in astrobiology. The study of cosmic dust continues to challenge and expand our understanding of the universe, as each new discovery reveals additional layers of complexity. Dust is not simply a passive component of space, it is a dynamic and active participant in the processes that govern the cosmos. Its presence alters light, shields planets, catalyzes chemical reactions, and contributes to the formation of stars and planets. Far from being an obstacle to our understanding of the universe, cosmic dust offers clues that, when deciphered, provide profound insights into the origins, evolution, and interconnectedness of all cosmic entities. As we move forward, missions aimed at capturing and studying cosmic dust will likely uncover even more surprises. The cosmic dust that settles on Earth, whether from distant interstellar clouds or the far reaches of the solar system, contains particles that carry with them the history of stellar evolution, galactic processes, and perhaps even clues to the conditions that led to life. These particles are messengers from the far reaches of space, each one contributing a unique piece to the cosmic puzzle. In this endless cycle of creation and destruction, dust particles play an enduring role, reminding us of the constant flux of the cosmos. As stars form, live, and die, their material is recycled, becoming the dust that shapes new worlds. This interconnectedness reflects a broader theme of unity in the universe, where every part of the cosmos is woven into a larger narrative. Cosmic dust, often overlooked, is a fundamental thread in this tapestry, binding together the past, present, and future of the universe. The study of cosmic dust and debris continues to push the boundaries of our knowledge, inviting us to explore not just the stars and galaxies but the tiny particles that bridge these vast structures. As we continue to explore these particles, we gain deeper insights into the processes that govern the cosmos, challenging our understanding and inspiring us to seek new answers to age-old questions. In the end, cosmic dust is more than mere particles. It is a symbol of the universe's ceaseless creativity, resilience, and interconnectedness, and a reminder of the mysteries that still lie beyond our reach. Cosmic dust serves as an unassuming yet essential architect of the universe, weaving itself into the fabric of space in ways that shape not only the structure of galaxies and planetary systems, but also the very possibilities for life. This stardust, born from the remnants of ancient stars and woven into the interstellar medium, reflects a deep interconnectedness where each speck plays a crucial role in the cosmos's endless cycles of creation, destruction, and rebirth. The journey of cosmic dust begins in the hearts of stars. When massive stars exhaust their nuclear fuel, they often explode as supernovae, scattering elements such as carbon, oxygen, silicon, and iron into space. These elements cool and condense to form solid grains, particles of dust that carry within them the chemical fingerprints of their stellar origins. Over time, these grains are mixed into the interstellar medium, the vast, diffuse regions of gas and dust that exist between stars. Here, they drift and wander, sometimes merging with clouds of molecular gas, which may eventually collapse to form new stars and planets. Thus, the dust that once resided within stars becomes the seeds of future solar systems, carrying with it the raw materials essential for planet building and potentially life itself. This cycle of dust formation, destruction, and rebirth is central to understanding the life cycles of stars and the evolution of galaxies. Dust particles play a catalytic role in cooling down molecular clouds, a process that enables the collapse of gas and dust into new stars. Without dust, the intense heat generated by collapsing gas would likely prevent stars from forming, as the necessary cooling mechanism would be absent. Thus, dust is not merely a byproduct of stellar death, it is a facilitator of stellar birth, bridging the end of one star's life with the beginning of another. In this way, cosmic dust acts as a cosmic recycling agent, ensuring that the materials forged in one generation of stars are available to fuel the next. As we examine the formation of planetary systems, the role of dust becomes even more intriguing. In the early stages of star formation, dust gathers in a rotating disk of gas and material around the young star. Over time, dust grains collide and stick together, forming larger clumps that eventually coalesce into planetesimals, the building blocks of planets. This process, known as accretion, transforms individual dust particles into planets, moons, and other bodies, giving rise to the complex architectures we observe in planetary systems today. This process illustrates the extraordinary journey of dust, from microscopic particles to planets, moons, and possibly life-bearing worlds. The study of cosmic dust also offers clues about the chemical environment in which planets form, as the composition of dust influences the types of molecules available for life. Many of the complex organic molecules necessary for life, such as amino acids and nucleotides, are believed to form on the surfaces of dust grains in cold, dense regions of molecular clouds. These molecules are then incorporated into the icy bodies that populate the outer regions of solar systems, such as comets and asteroids. When these icy bodies collide with young planets, they may deliver these organic compounds, potentially seeding the planets with the building blocks of life. This process suggests that the dust within molecular clouds could play an essential role in fostering the conditions necessary for life, making it an active participant in the grand experiment of the cosmos. Our understanding of cosmic dust has advanced significantly with recent technological innovations, particularly in the field of infrared astronomy. Instruments such as the James Webb Space Telescope, JWST, and the Atacama Large Millimeter/Submillimeter Array, ALMA, have allowed astronomers to observe dust in unprecedented detail. Infrared and submillimeter wavelengths penetrate dense dust clouds, revealing the structures and dynamics hidden within. These observations have unveiled intricate networks of filaments, knots, and voids, highlighting the complex interactions between dust, gas, and radiation. The data gathered from these telescopes provide a clearer picture of how dust shapes star-forming regions, influences galaxy morphology, and interacts with intense radiation from young stars. However, cosmic dust is not merely a passive participant in cosmic evolution. It also poses a significant challenge to our observational capabilities. Dust clouds absorb and scatter visible light, obscuring our view of distant stars, galaxies, and other celestial objects. This effect, known as extinction, complicates efforts to measure the true brightness and distance of objects, especially those located in or behind dense dust regions. Additionally, dust selectively scatters shorter, blue, wavelengths, causing distant objects to appear redder than they actually are, a phenomenon called reddening. To correct for these effects, astronomers must rely on complex models that account for the dust's composition, distribution, and grain size, allowing for more accurate measurements of celestial distances and properties. The impact of dust on observations goes beyond obscuration and reddening. Dust emission in the infrared spectrum can also interfere with observations of faint, distant objects. This infrared background noise is caused by the re-radiation of absorbed starlight by dust grains, which emit thermal radiation at infrared wavelengths. In the context of galaxy formation, this infrared glow provides valuable information about star-forming regions and dusty starburst galaxies, but it also creates challenges for astronomers attempting to observe faint objects in the background. To mitigate these effects, astronomers must use sophisticated filtering techniques and sometimes place telescopes outside Earth's atmosphere, where the effects of both cosmic and terrestrial dust are minimized. Despite these challenges, the presence of cosmic dust offers unparalleled insights into the processes that govern cosmic evolution. Dust grains contain records of their chemical and isotopic compositions, revealing details about their origins and the environments through which they have traveled. By studying these compositions, scientists can trace the dust's journey across space and time, uncovering evidence of supernova explosions, ancient star-forming regions, and the dynamics of galactic recycling processes. This information helps build a timeline of cosmic events, offering a glimpse into the life histories of galaxies and the stars within them. Cosmic dust also provides a window into the conditions of the early universe. Observations have detected dust in galaxies that existed just 1 billion years after the Big Bang, indicating that star formation and supernova events had already enriched the universe with heavy elements. This finding challenges previous assumptions that the early universe was devoid of complex chemical compounds and suggests that galaxy formation may have been a more rapid and dynamic process than previously thought. The presence of dust in these ancient galaxies highlights the rapid evolution of the first stars, whose explosive deaths contributed the raw materials needed for subsequent generations of stars and galaxies. In our own solar system, dust plays a crucial role in shaping planetary environments. For instance, the zodiacal light, a faint glow seen in the night sky along the plane of the ecliptic, is caused by sunlight scattering off interplanetary dust. This dust, a mixture of particles from comets, asteroids, and interstellar grains, orbits the Sun and interacts with solar radiation and the solar wind. These interactions gradually alter the dust's orbital paths, leading to complex and dynamic behavior within the inner solar system. Moreover, the dust environment of a planetary system can have significant implications for the formation and stability of planets, as dust influences the migration of planetesimals and can create structures such as asteroid belts and cometary reservoirs. The role of dust in planetary systems extends beyond its physical interactions. Dust may also play a chemical role by contributing organic compounds to planets with atmospheres and surfaces conducive to life. On Earth, for example, interplanetary dust particles continuously settle through the atmosphere, delivering trace amounts of extraterrestrial material to the planet's surface. These particles, while small in quantity, contain isotopic and chemical signatures that link them to specific regions of the solar system or even to other star systems. By analyzing the composition of these particles, scientists gain valuable insights into the chemical diversity of the solar system and the potential pathways through which organic compounds could have reached early Earth. The study of cosmic dust and its effects on planetary systems, stars, and galaxies is an ever-evolving field, revealing new mysteries with each technological advance. As we continue to explore and observe the universe, cosmic dust remains a constant companion, guiding us through the stories of stellar birth and death, planetary formation, and the potential origins of life. Its journey through the cosmos, from star to star and planet to planet, underscores the profound interconnectedness of all matter, reminding us that we, too, are part of this grand cosmic cycle. Ultimately, the study of cosmic dust and debris is a testament to the intricate beauty and complexity of the universe, where even the smallest particles can wield immense influence over cosmic phenomena. Through its interactions with light, its role in star and planet formation, and its potential to carry life's building blocks across the cosmos, dust emerges as one of the universe's most vital ingredients. Its presence may obscure our view at times, yet it also reveals the subtle ways in which the universe renews itself, continually creating and transforming in the dance of stardust and energy. In this delicate balance of creation and destruction, cosmic dust serves as both witness and participant, shaping the cosmos while bearing the imprints of its history. Every speck of dust that drifts through space tells a story of distant stars, ancient supernovae, and the slow, steady evolution of galaxies and planetary systems. It is a story that speaks to the fundamental unity of all things, where even the smallest particles play their part in the vast, interconnected tapestry of existence. And as we uncover more about these particles, we come closer to understanding not just the cosmos but our own place within it, as beings born from stardust and bound to the endless cycle of the universe. The study of cosmic dust continues to push the boundaries of our understanding, leading to even deeper questions about the role it plays in the evolution of the universe. One of the most intriguing aspects of cosmic dust lies in its ability to serve as a catalyst for the formation of complex organic molecules, which might have profound implications for the origins of life. In the cold, dense regions of interstellar space, where temperatures can drop to just a few degrees above absolute zero, dust particles become coated with ices made of water, carbon monoxide, methane, and other simple molecules. Under these conditions, the surfaces of dust grains can facilitate chemical reactions that lead to the formation of more complex compounds. Over time, cosmic radiation and ultraviolet light from nearby stars interact with these icy mantles, driving chemical reactions that produce molecules such as amino acids, sugars, and other prebiotic compounds. These molecules are critical building blocks for life as we know it, suggesting that the ingredients for life could form in the harshest, most distant reaches of space. This process turns cosmic dust into a kind of cosmic laboratory, where the chemistry of life can begin even before planets form. When these dust-laden ices are incorporated into forming planets, they deliver a payload of organic material that could potentially kickstart biological processes under the right conditions. The possibility that life's building blocks could be synthesized in space has profound implications for the question of whether life exists elsewhere in the universe. If cosmic dust is responsible for seeding planetary systems with organic compounds, then the basic ingredients for life might be widely distributed across the cosmos, increasing the likelihood that life could emerge on other planets. This Panspermia hypothesis suggests that life, or at least the components necessary for life, could be spread across the universe via comets, asteroids, and interstellar dust particles, allowing it to potentially flourish in diverse environments far beyond Earth. Interstellar dust and cosmic debris also play a significant role in shaping the environments around young stars, especially those in star-forming regions. As stars form within molecular clouds, powerful stellar winds and radiation pressure blow away nearby gas and dust, sculpting cavities and complex structures within the cloud. This feedback process from young stars affects the density and distribution of dust, altering the conditions under which new stars and planetary systems can form. Regions of particularly dense dust can shield molecules from the intense radiation of young stars, allowing these molecules to persist and potentially participate in the formation of new stars and planets. In certain star-forming regions, dust clouds are so dense that they block nearly all visible light, creating dark nebulae, mysterious, pitch-black clouds that appear to be voids in the night sky. These regions can only be observed using infrared and radio wavelengths, which penetrate the dense dust and reveal the hidden star-forming activity within. Observing these regions provides astronomers with insights into the earliest stages of star formation and the role of dust in creating environments conducive to planet formation. On larger scales, cosmic dust influences not only individual stars and planetary systems, but also the structure of galaxies. Dust lanes, vast regions of interstellar dust, are a common feature of spiral galaxies, including our own Milky Way. These lanes often appear as dark streaks across the bright, star-filled arms of galaxies, absorbing and scattering visible light. The presence of dust in these lanes plays a crucial role in regulating the star formation rate within galaxies. Dust clouds can act as reservoirs for the cold, dense gas that eventually collapses to form stars, while also shielding molecular clouds from the harsh radiation of nearby stars. Dust also participates in the life cycle of galaxies by contributing to the feedback processes that regulate star formation. Supernova explosions, stellar winds, and radiation pressure from massive stars stir up the dust and gas within galaxies, distributing these materials across vast distances. This redistribution can halt star formation in certain regions while triggering it in others, creating a complex interplay between dust, gas, and star formation that drives the evolution of galaxies over billions of years. As galaxies interact and merge, their dust and gas clouds are thrown into chaotic configurations, leading to bursts of star formation known as starbursts. These intense periods of star formation can consume much of the galaxy's gas and dust, rapidly depleting the materials necessary for future star formation. The dust generated in these starbursts contributes to the intergalactic medium, the vast regions of space between galaxies, where it may eventually find its way into new star-forming regions. This process highlights the role of dust in connecting galaxies and spreading the elements forged in stars across the cosmos. In the distant reaches of the universe, where galaxies formed in the early epochs following the Big Bang, cosmic dust offers a window into the history of star formation. Observing the dust content of these ancient galaxies reveals information about the rate of star formation in the early universe and the enrichment of galaxies with heavy elements. High levels of dust in early galaxies suggest that supernovae and massive stars played a significant role in rapidly enriching the interstellar medium, contributing to the formation of dust and the subsequent evolution of galaxies. One of the greatest challenges in studying cosmic dust is its dual role as both a creator and an obscurer of light. While dust provides valuable insights into the processes of star and planet formation, it also complicates observations by obscuring distant objects. Astronomers have developed sophisticated techniques to account for this, such as using different wavelengths of light to peer through dust clouds. Radio, infrared, and submillimeter wavelengths, for instance, can pass through dust, allowing astronomers to study the structures within dense regions of space that are otherwise invisible. These techniques have revealed entire populations of stars, protostars, and star-forming regions hidden within dust clouds, providing a more complete picture of the universe's star-forming activities. Despite these advances, certain regions of space remain challenging to study due to the sheer density of dust and gas. The galactic center of the Milky Way, for example, is shrouded in a thick veil of dust, making it difficult to observe the supermassive black hole at its core. Only by observing at very long wavelengths, such as those used in radio astronomy, can astronomers penetrate this veil and gather data on the dynamics of the galactic core. These observations are critical for understanding the role of supermassive black holes in galaxy evolution and the interactions between black holes, stars, and dust. Dust also plays a role in the formation of planetary rings and belts, such as those found around Jupiter, Saturn, Uranus, and Neptune. These rings are composed of ice, rock, and dust particles that orbit the planets, creating complex and dynamic systems that are influenced by the gravitational forces of nearby moons and the planets themselves. Observing these rings provides valuable insights into the processes that govern the formation and stability of planetary systems, as well as the interactions between dust and larger bodies within those systems. In recent years, the study of exoplanetary dust disks, rings of dust surrounding distant stars, has provided a new frontier in our understanding of planet formation. Observations of these disks reveal structures such as gaps, rings, and spiral arms, which may indicate the presence of forming planets. The dust within these disks acts as a tracer for the distribution of material around the star, allowing astronomers to infer the presence and properties of exoplanets that are otherwise too faint to observe directly. These findings have expanded our understanding of how planets form in diverse environments, and how dust contributes to the architecture of planetary systems beyond our own. The study of cosmic dust also has implications for understanding the nature of dark matter, the mysterious substance that makes up the majority of the universe's mass. Although dust itself is not a form of dark matter, observations of dust and gas can help map the gravitational effects of dark matter on galaxies. By studying how dust and gas move within galaxies, astronomers can infer the distribution of dark matter and gain insights into its influence on galactic structures. This research underscores the interconnectedness of all cosmic phenomena, where the study of one component, such as dust, can reveal information about the broader framework of the universe. In this vast and intricate cosmic web, cosmic dust serves as a bridge between the stars, galaxies, and planets, connecting them in a cycle of creation and destruction that spans billions of years. From its role in star formation to its influence on planetary systems, cosmic dust embodies the relentless dynamism of the cosmos, where even the smallest particles play crucial roles in the grand architecture of the universe. Its presence reminds us that the universe is not only a place of vast empty spaces but also a realm filled with unseen structures, hidden processes, and endless possibilities. As we continue to explore and understand cosmic dust, we unlock new perspectives on the origins and evolution of stars, planets, and even life itself. In every observation, every discovery, and every analysis of cosmic dust, we come closer to unraveling the mysteries of the cosmos and our place within it, as beings forged from the very particles that drift through space, forever bound to the endless cycle of creation and transformation that defines the universe. As we deepen our exploration of cosmic dust, we encounter yet another layer of its significance, its capacity to reveal information about the physical conditions, chemical processes, and magnetic fields in the cosmos. Each tiny particle serves as a cosmic archive, preserving a record of the conditions in which it was formed, altered, or transported. This archived information enables astronomers to investigate the histories of stars, planets, and galaxies in remarkable detail, shedding light on both recent and ancient cosmic events. When studying cosmic dust, one area of particular interest is the investigation of polarized light. Dust particles, due to their irregular shapes and alignment with magnetic fields, polarize light that passes through them. This polarized light provides crucial data on the magnetic fields within galaxies and molecular clouds. Magnetic fields are notoriously difficult to observe directly, but by analyzing the polarization patterns of light, astronomers can deduce their structure and strength. This insight is vital because magnetic fields play a fundamental role in controlling the behavior of gas and dust, influencing star formation and the overall dynamics of galaxies. Furthermore, cosmic dust particles come in a fascinating range of sizes and compositions, from tiny nanoparticles to sizable clumps of ice and rock. These variations provide a unique window into the diverse chemical environments of space. Dust particles closer to stars are often stripped of their icy coatings, leaving behind core elements like silicates or carbon compounds. However, in colder, more distant regions, these particles can maintain ices rich in carbon dioxide, methane, ammonia, and even complex organic molecules. By analyzing these particles, astronomers can study how different environmental factors, such as radiation and temperature, shape the chemical evolution of dust over time. Observations of cosmic dust across multiple wavelengths, from visible light to X-rays, have revealed that dust can vary widely between different galactic environments. In the densely packed star-forming regions of spiral galaxies, dust tends to be highly enriched with heavy elements like silicon and iron, a testament to the generations of stars that have lived and died within these galaxies. In contrast, the dust in elliptical galaxies, galaxies that have often exhausted their star-forming material, is relatively sparse and tends to contain fewer heavy elements. These differences provide a cosmic fingerprint, helping astronomers trace the star formation history and chemical evolution of different types of galaxies. In the context of planetary systems, cosmic dust plays a fundamental role in shaping the structures and atmospheres of planets. For instance, the early stages of planet formation are thought to occur within protoplanetary disks, where cosmic dust grains collide, stick together, and gradually grow into larger bodies. Over time, these aggregates become planetesimals, the building blocks of planets. The efficiency and composition of this process depend on the properties of the dust within the disk, as well as the surrounding conditions. Certain types of dust are more likely to coalesce, influencing which materials are incorporated into emerging planets. As such, dust composition can ultimately determine the types of planets that form and the likelihood of creating environments conducive to life. Dust also continues to influence planetary bodies long after their formation. For planets with atmospheres, such as Earth, incoming cosmic dust, mostly in the form of meteoric dust, interacts with atmospheric particles, often forming complex chemical reactions. This interaction can contribute to atmospheric phenomena such as noctilucent clouds, which are formed by ice crystals around particles of cosmic dust high in Earth's mesosphere. These clouds are not only beautiful but also serve as indicators of changes in our atmosphere, providing clues about climate variations and the impact of cosmic particles on atmospheric dynamics. Beyond Earth, cosmic dust significantly impacts the atmospheres of other planets and moons. For example, on Mars, dust storms sometimes engulf the entire planet, dramatically affecting its surface temperature and atmospheric circulation. Understanding the behavior and properties of Martian dust is essential for predicting these storms and assessing their impact on future exploration missions. In Saturn's system, the dust within its rings interacts with its moons, generating complex exchanges of material that shape the surfaces and atmospheres of those moons. Through these processes, cosmic dust contributes to the dynamic and ever-changing nature of planetary bodies throughout the solar system. The study of cosmic dust has even influenced our understanding of the solar wind, the stream of charged particles flowing from the Sun. As cosmic dust enters the solar system, it encounters the solar wind, which causes dust particles to slow down, change course, or even vaporize. This interaction helps scientists better understand the properties of the solar wind and its effects on both cosmic dust and planetary atmospheres. For example, charged dust particles are deflected by the solar wind, creating a dust-free zone around the Sun and generating features like the solar corona. These phenomena are key to understanding the behavior of dust in the inner solar system, as well as the influence of stellar winds in other star systems. Moreover, cosmic dust sheds light on the life cycle of matter in the universe. In a process known as recycling, dust produced by stars in the form of stellar winds and supernova remnants gradually enriches interstellar clouds, providing raw materials for new stars and planets. This cycle of dust generation, accumulation, and redistribution contributes to the cosmic ecosystem, ensuring that the elements forged in stars are not lost but instead incorporated into new celestial bodies. This recycling process is fundamental to the evolution of the universe, as it perpetuates the creation of stars, planets, and potentially habitable environments. The next frontier in studying cosmic dust involves leveraging advanced technologies, such as next-generation telescopes, to capture even more detailed observations. Space observatories like the James Webb Space Telescope, JWST, are poised to revolutionize our understanding of cosmic dust by observing it in unprecedented detail across the infrared spectrum. With its ability to penetrate dense dust clouds and analyze the chemical makeup of distant cosmic regions, JWST will likely uncover new insights into the composition and role of cosmic dust in star and planet formation. Similarly, missions like the European Space Agency's Gaia Observatory and the Square Kilometre Array (SKA) are expanding our ability to map and analyze dust on a galactic scale. Gaia's precise measurements of star positions and motions are helping astronomers map the distribution of dust within the Milky Way, while the SKA, an array of radio telescopes, will allow scientists to study dust and gas in unprecedented detail, even in regions that are challenging to observe with optical telescopes. Together, these observatories are creating a more complete picture of the role of dust throughout the galaxy and beyond. Our growing understanding of cosmic dust also has implications for future space exploration. As humanity plans missions to explore more distant regions of our solar system and beyond, knowledge of dust dynamics will be critical for ensuring the safety of spacecraft and astronauts. Dust particles, even at microscopic sizes, can pose serious threats to spacecraft, particularly at high velocities where impacts can cause damage to instruments and protective coatings. Understanding the distribution and behavior of cosmic dust is thus essential for designing resilient spacecraft capable of withstanding these conditions. In the search for extraterrestrial life, cosmic dust holds promise as a potential medium through which signs of life could be detected beyond our planet. Dust grains can carry with them traces of organic molecules or isotopic signatures indicative of biological processes. Future missions may aim to capture and analyze cosmic dust particles, either in space or from the surfaces of other celestial bodies, to search for potential biosignatures or chemical indicators of life. This approach could expand our search for life beyond the confines of traditional planets or moons, offering new possibilities for discovering evidence of life across the cosmos. Cosmic dust remains an enigmatic yet profoundly influential component of the universe. It plays a role in almost every major cosmic process, from star and planet formation to the evolution of galaxies. As our knowledge of dust expands, we continue to unveil the complexity of the universe and our own origins. The particles that drift through space, seemingly insignificant on their own, collectively shape the very fabric of the cosmos. They remind us that even the smallest elements can have far-reaching impacts, connecting distant stars, galaxies, and potentially life itself in a vast, interwoven cosmic tapestry. Our pursuit of understanding cosmic dust is a testament to humanity's insatiable curiosity. Each discovery brings us one step closer to comprehending the mysteries of the universe, highlighting the interconnectedness of all matter. In every particle of cosmic dust lies a fragment of history, a clue to our origins, and a glimpse into the infinite possibilities of the cosmos. The story of cosmic dust is ultimately the story of the cosmos itself, a saga of creation, destruction, and rebirth told through the silent, persistent drift of these tiny particles across the universe. From the earliest moments after the Big Bang, when the first elements like hydrogen and helium were forged, to the formation of complex organic compounds in the icy depths of interstellar space, cosmic dust has continuously evolved. Each particle tells a unique chapter in this grand story, embodying countless cycles of birth, transformation, and dispersal as it moves through stars, nebulae, and planets. In star-forming regions, cosmic dust acts as a cooling agent, helping gas clouds collapse under their own gravity to ignite new stars. Without the presence of dust, the gas would remain too hot and diffuse to form stars efficiently. Dust particles absorb heat from the surrounding gas and radiate it away, allowing the gas to cool and condense. As these young stars begin to shine, they irradiate the surrounding dust, causing it to glow and become visible as a reflection nebula. In this way, cosmic dust both facilitates and signals the birth of stars, playing a crucial role in shaping the life cycle of celestial bodies. In some cases, cosmic dust serves as a foundation for new life. Organic compounds found in cosmic dust, such as amino acids and simple sugars, are the building blocks of life as we know it. Researchers have discovered these molecules in meteorites and comets, suggesting that the raw materials for life may be scattered throughout the cosmos, potentially even seeding young planets. This idea, known as Panspermia, proposes that life, or at least its precursors, could travel between worlds via cosmic dust or meteorites. While still a hypothesis, it raises the possibility that cosmic dust may have contributed to the origin of life on Earth, and perhaps even on other planets. As cosmic dust particles wander through space, they encounter a variety of forces that shape their journeys. Gravity, radiation pressure, and magnetic fields all influence the movement and distribution of dust. For instance, radiation pressure from stars can push dust particles away, especially those near the inner regions of planetary systems. This force acts like a gentle wind, carrying dust particles outward and creating a tail of dust around stars, reminiscent of a comet's tail. The effects of these forces result in the creation of dust rings, clouds, and other structures around stars, which can be observed with advanced telescopes. The presence of cosmic dust complicates astronomical observations, as it absorbs and scatters light, particularly at visible wavelengths. This interference can obscure distant objects, making it challenging for astronomers to observe the interiors of dense dust clouds or distant galaxies. However, astronomers have found ways to circumvent these limitations. By observing in the infrared or radio wavelengths, which penetrate dust clouds more effectively than visible light, researchers can peer into these obscured regions and study the processes occurring within them. In recent years, scientists have developed new techniques to examine the chemical fingerprints of cosmic dust, including isotopic analysis. Isotopes, atoms of the same element with different numbers of neutrons, can reveal details about the processes that formed the dust. For example, The ratios of oxygen or carbon isotopes in a particle can indicate whether it originated in a supernova or a planetary nebula. This isotopic data provides a kind of cosmic signature, linking dust particles to specific stellar events and enabling researchers to reconstruct the histories of distant stars and galaxies. Interstellar dust also influences the evolution of galaxies. In large galaxies like the Milky Way, cosmic dust congregates in spiral arms, where it interacts with gas clouds to fuel ongoing star formation. The dust in these regions absorbs ultraviolet and visible light from young, hot stars and re-emits it in the infrared spectrum. This re-radiation of energy not only affects the appearance of galaxies but also contributes to their thermal balance and energy distribution. Galaxies rich in dust are typically bright in the infrared, and studying this infrared emission provides insights into the rates of star formation and the characteristics of the galaxy's interstellar medium. One particularly intriguing phenomenon associated with cosmic dust is the concept of dust storms in space. Dust storms are most commonly associated with planets, particularly Mars, where massive storms can cover the entire planet. However, in some regions of the galaxy, large clouds of dust can create storms, as they are pushed by stellar winds or interact with magnetic fields. These cosmic dust storms can stretch for light years, forming enormous structures that influence the movement of gas and dust on a galactic scale. Understanding these storms helps astronomers comprehend the forces shaping galaxies and star-forming regions. On the scale of individual star systems, dust disks around young stars, known as protoplanetary disks, are the birthplaces of planets. These disks are primarily composed of gas and dust, which orbit the star in a flattened, rotating disk. Over time, dust particles within these disks collide and stick together, forming larger clumps that eventually grow into planetesimals and later, into full-fledged planets. The composition and distribution of dust in these disks can influence the types of planets that form, as well as their orbital characteristics. This process is particularly evident in systems with debris disks, where remnants of dust and rock continue to orbit the star even after planets have formed. Observations of debris disks around stars like Vega and Fomalhaut have provided a glimpse into the late stages of planet formation. These disks are typically rich in small dust particles that are constantly being replenished by collisions between larger bodies, such as comets and asteroids. The study of these disks has revealed the existence of unseen planets, whose gravitational influence shapes the dust into rings or gaps, similar to the structure of Saturn's rings. By analyzing these patterns, astronomers can infer the presence and properties of planets that might otherwise be undetectable. Cosmic dust has also provided valuable information about the early solar system. Meteorites found on Earth often contain tiny particles of pre-solar dust, grains that predate the formation of our Sun and planets. These grains are thought to have originated in distant stars and supernovae, only to be later incorporated into the forming solar system. By analyzing these pre-solar grains, scientists have been able to study the chemical environments of ancient stars and gain insight into the processes that shaped our solar system billions of years ago. The study of cosmic dust is not only limited to natural phenomena but also has practical applications for space exploration. Dust particles pose a challenge for spacecraft and instruments, as high-velocity impacts with dust can damage sensitive equipment. To mitigate this risk, space missions such as NASA's Parker Solar Probe are equipped with dust shields to protect against collisions with dust particles near the Sun. Similarly, understanding the behavior of dust is essential for planning long-duration missions to the Moon, Mars, or beyond, where dust can pose health risks to astronauts and affect equipment reliability. As technology advances, scientists continue to develop innovative methods to collect and study cosmic dust. One such mission was NASA's Stardust spacecraft, which traveled to the comet Wild 2 and returned samples of cometary dust to Earth. The analysis of these samples provided a wealth of information about the composition of cometary dust and the conditions in the early solar system. Missions like Stardust paved the way for future exploration, potentially enabling scientists to gather dust samples from other regions of the solar system, or even from interstellar space. The study of cosmic dust has come a long way, from early observations of dark patches in the Milky Way to sophisticated analyses of dust grains collected by space missions. Yet there is still much to learn about the role of dust in the universe. Each discovery opens new questions, as scientists strive to unravel the complexities of dust dynamics, composition, and its influence on cosmic evolution. As our understanding of dust deepens, so too does our understanding of the processes that have shaped, and continue to shape, the cosmos. Cosmic dust is both a participant and a witness in the cosmic dance, influencing the birth of stars, the formation of planets, and perhaps even the emergence of life. The secrets it holds are as varied as the stars themselves, each particle a relic of a distant place or an ancient time. In a universe filled with wonders, cosmic dust reminds us that sometimes, the smallest elements can hold the greatest mysteries. As we continue to probe the mysteries of cosmic dust and cosmic debris, the scale at which these particles influence the universe becomes even more profound. The interplay between cosmic dust and cosmic debris contributes to the ongoing evolution of galaxies, stars, and planetary systems in ways that remain deeply intertwined with the larger dynamics of the cosmos. One of the most fascinating aspects of cosmic dust is its role in the interstellar medium, the vast, seemingly empty space between stars. This space is far from empty, as it is filled with gas and dust particles. The density of the interstellar medium is incredibly low, with just a few particles per cubic centimeter, but it is still crucial for understanding the evolution of galaxies. Cosmic dust grains serve as seeds for the formation of molecules, with certain regions of space becoming dense enough to form molecular clouds. These clouds are the birthplaces of new stars, and they play a key role in the recycling of matter in galaxies. Over time, the cycle of star birth and death releases heavier elements into the interstellar medium, enriching it and enabling the creation of more complex structures. The study of cosmic dust also sheds light on the history of the universe itself. Many of the particles we observe today are remnants of stars that lived and died billions of years ago. These particles, particularly those that originated in supernovae, carry with them information about the nucleosynthesis processes that took place within those stars. By studying the isotopic ratios in cosmic dust, scientists can gain insight into the composition of distant stellar systems and track the evolution of matter throughout the history of the universe. Cosmic dust acts as a time capsule, preserving clues about the early universe and the processes that led to the formation of galaxies, stars, and planets. Beyond the stellar and galactic scales, cosmic dust also plays a significant role in shaping the environments of individual planets. For example, in the early stages of planetary formation, dust and gas in protoplanetary disks collide and coalesce to form larger bodies. These bodies, called planetesimals, eventually accumulate to form planets. As they grow, they continue to interact with surrounding dust and debris, sometimes sweeping it up and sometimes colliding with it, adding layers of material to their surfaces. This process can lead to the creation of moons, rings, and other planetary features that contribute to the unique characteristics of a given planet or moon. For example, Saturn's rings are composed primarily of dust and debris left over from shattered moons or comets, providing a lasting testament to the destructive and creative forces at work in the solar system. Dust's role in planetary systems extends beyond the formation of planets. In the case of Earth, cosmic dust has been a continuous presence throughout the planet's history. Some of the dust particles found on Earth are remnants of comets, or asteroids that have collided with the planet. These collisions, though rare on human timescales, have had significant impacts on Earth's history. Large impacts are believed to have played a role in mass extinctions and the formation of craters, like the one that formed the Chicxulub crater in Mexico, which is associated with the mass extinction event that wiped out the dinosaurs. The presence of cosmic dust in Earth's atmosphere also contributes to the phenomenon known as cosmic rainfall, where tiny particles fall to the surface of the Earth every year, adding to the planet's material balance. Interestingly, Earth's atmosphere itself plays a role in dust's journey across space. The solar wind, a stream of charged particles emitted by the sun, interacts with the interstellar medium and creates a dust cloud that surrounds the solar system. This is known as the heliosphere, and it extends well beyond the orbit of Pluto, As cosmic dust enters the solar system, it interacts with this protective bubble, slowing down and redirecting its path toward the inner planets. This interaction between solar wind and cosmic dust can lead to the formation of dust tails around comets, as well as contribute to the overall dynamics of the solar system. The effects of cosmic dust are not confined solely to planetary systems and galaxies. They also influence our understanding of cosmic phenomena. One of the key challenges in astronomy is the observation of distant objects, particularly when those objects are located within dense regions of space filled with dust. Observing distant stars, galaxies, or even the light from the early universe can be complicated by the presence of dust, which absorbs and scatters light. This dust extinction effect reduces the visibility of distant objects, particularly in the ultraviolet and visible wavelengths. To circumvent this issue, astronomers rely on infrared telescopes, which can penetrate the dust and reveal the objects hidden within. By using infrared data, astronomers can study the formation of stars and galaxies in distant parts of the universe, providing insight into the early stages of cosmic evolution. Dust also contributes to the understanding of dark matter, a mysterious substance that makes up a significant portion of the universe's mass but does not emit, absorb, or reflect light. One of the leading theories in the study of dark matter suggests that cosmic dust may interact with dark matter in ways that could help scientists detect its presence. Researchers are investigating the possibility that dark matter particles may be embedded within cosmic dust, providing a unique opportunity to study dark matter indirectly. While this research is still in its early stages, it highlights the intricate connections between cosmic dust and the larger forces of the universe. The role of cosmic dust is particularly apparent in the process of stellar death. When stars exhaust their nuclear fuel, they undergo dramatic transformations. Low and medium mass stars expand into red giants and shed their outer layers, releasing vast amounts of dust and gas into space. This material enriches the interstellar medium, helping to create new generations of stars. High-mass stars, on the other hand, explode in supernovae, releasing even more dust and debris into space. The dust produced by these stellar explosions is rich in heavy elements like iron and silicon, which are essential for the formation of planets and other bodies. The remnants of supernovae provide the raw materials for future star systems, and the cycle continues, with dust playing an essential role in the ongoing evolution of galaxies and planetary bodies. The study of cosmic dust has revealed that even the smallest particles in the universe can have profound effects on the structures we observe. From influencing the formation of planets and stars to altering the way we perceive distant objects, cosmic dust plays a fundamental role in shaping the universe. The particles that make up dust are often invisible to the naked eye, yet their impact is felt across the vast expanse of space. As our technology continues to advance, our ability to study and understand cosmic dust will only improve. Missions like the European Space Agency's Cosmic Dust Analyzer, which collects data on the composition of dust particles in the solar system, and the James Webb Space Telescope, which will observe the universe in infrared wavelengths, will provide even deeper insights into the nature of dust and its role in the cosmos. These tools will allow scientists to observe dust in greater detail, track its movements across the galaxy, and piece together the cosmic puzzle. In many ways, the study of cosmic dust is a reminder of the interconnectedness of the universe. What appears to be a minor detail, these tiny particles floating through the vast emptiness of space, turns out to be a key player in the grand story of the cosmos. Dust is part of the larger process of cosmic evolution, influencing the birth and death of stars, the formation of planets, and the very composition of galaxies. As we continue to explore the cosmos, we are reminded that space is not empty. It is filled with the remnants of stars and the building blocks of new ones, with dust and debris scattered across vast distances. Every particle, every grain of dust, holds a story. Together, they form a rich and complex narrative that shapes the universe and continues to reveal new mysteries to those willing to listen. As we delve deeper into the complex relationship between cosmic dust and the universe's larger processes, it becomes clear that these seemingly insignificant particles are far more than just a cosmic nuisance. They are fundamental to the formation and evolution of celestial bodies, serving as a medium through which the universe sustains its cyclical nature of creation and destruction. One of the most important areas where cosmic dust plays a pivotal role is in the formation of stars. Stars form in molecular clouds, dense, cold regions of space where dust and gas collide and accumulate. These clouds, often referred to as stellar nurseries, are rich in cosmic dust particles that provide the raw material necessary for star formation. As the gas and dust within a molecular cloud come together under the force of gravity, they begin to collapse inward, forming dense cores. These cores eventually heat up to the point where nuclear fusion can begin, and a new star is born. Without the dust particles acting as the seeds around which gas can gather, the process of star formation would be far less efficient, if not impossible. Cosmic dust not only plays a crucial role in the creation of stars, but also influences the death of these stars. When stars reach the end of their lives, they expel a tremendous amount of material into space, including vast quantities of dust. This can occur through various mechanisms, such as supernova explosions or the shedding of outer layers by less massive stars. The dust produced in these final stages of a star's life is rich in heavy elements, which are essential for the formation of planets and other celestial objects. The presence of this dust, enriched with the building blocks of life, elements like carbon, oxygen, and iron, ultimately leads to the formation of new generations of stars, planets, and moons. The cycle of dust production, spread, and eventual recapture by new stellar systems highlights the role of cosmic dust in the recycling of matter throughout the universe. Each star's life and death contributes to the material richness of the interstellar medium, feeding the formation of future star systems. This never-ending cycle of stellar birth, life, and death is intricately linked with the cosmic dust that forms the foundation of all matter in the universe. As this material circulates throughout galaxies, it undergoes continuous transformation, eventually contributing to the development of planetary systems and life itself. Dust plays a similar role in the formation and evolution of planetary systems. As protoplanetary disks surround newborn stars, they are composed of gas and dust particles. The dust particles in these disks collide and stick together, forming larger bodies over millions of years. These bodies, known as planetesimals, eventually collide and merge to form planets. During this process, cosmic dust serves as the building blocks of planets, and the debris left over from these collisions may go on to form moons, asteroids, and comets. The impact of cosmic dust on the development of planetary systems extends well beyond the formation of planets. It continues to influence the evolution of planetary bodies long after their formation. For example, dust impacts the development of planetary atmospheres. In the case of Earth, cosmic dust particles contribute to the planet's atmospheric chemistry by introducing elements and compounds that interact with the gases present in the atmosphere. This has implications for the planet's climate and the evolution of its surface. Some dust particles, for instance, contribute to the formation of clouds, which play a role in regulating the planet's temperature. Additionally, cosmic dust plays a role in the ongoing process of planetary bombardment, where dust particles from space collide with planets, adding material to their surfaces and sometimes even influencing their geological activity. On a larger scale, cosmic dust and debris influence the dynamics of galaxies themselves. The formation of new stars and planets often occurs within dusty regions of galaxies, where gas and dust clouds can condense and collapse to form new celestial objects. The motion of these clouds of dust and gas through the galaxy can impact the shape and evolution of the galaxy as a whole. Dust can also act as a barrier between different regions of a galaxy, blocking light from distant stars and altering the appearance of the galaxy when viewed from Earth. In fact, much of the visible universe is obscured by cosmic dust, making it difficult for astronomers to observe distant objects in their entirety. This is one of the reasons why astronomers use telescopes that observe in wavelengths such as infrared, which can penetrate dust clouds and reveal hidden objects. In this way, cosmic dust does not merely obscure our vision, it shapes the very structure of galaxies and determines what we can observe in the universe. It forces us to use innovative methods to study the cosmos, allowing for the discovery of objects and phenomena that would otherwise be invisible. Through dust, we gain access to the most distant and ancient corners of the universe, allowing us to understand the processes that have shaped galaxies, stars, and planetary systems over billions of years. While dust plays a crucial role in the formation of stars and planets, its impact goes beyond just the birth of celestial bodies. The presence of cosmic dust influences the chemical composition of planets, moons, and other bodies in the solar system. As dust settles on planetary surfaces, it can be altered by the interaction with solar radiation and other environmental factors, contributing to the chemical diversity seen across planets. In the case of Earth, cosmic dust is believed to have played a role in the planet's early chemistry, particularly in the formation of water and organic compounds. As these materials mixed with Earth's primordial atmosphere and oceans, they laid the foundation for the emergence of life. On Earth, we are constantly bombarded by cosmic dust. Every year, an estimated 40,000 tons of cosmic dust fall to Earth, much of it invisible to the naked eye. This dust is made up of tiny particles, some no larger than grains of sand, while others are microscopic in size. Despite its small scale, this cosmic rain has a profound impact on Earth's environment. Cosmic dust interacts with the Earth's atmosphere, contributing to cloud formation and influencing the planet's weather patterns. Dust particles from space can even affect the Earth's climate by influencing the amount of sunlight that reaches the surface. Interestingly, the presence of cosmic dust on Earth has also been linked to various scientific discoveries. Studies of cosmic dust collected from the Earth's atmosphere have provided valuable information about the composition of asteroids, comets, and other celestial bodies. In some cases, the analysis of cosmic dust has even revealed the presence of organic molecules, offering clues about the potential for life elsewhere in the universe. These discoveries demonstrate that cosmic dust is not just a passive observer of cosmic events but an active participant in the processes that shape the universe. Beyond the solar system, cosmic dust is a key element in the study of exoplanets, the planets that orbit stars beyond our Sun. As scientists observe distant exoplanets, they often encounter challenges due to the presence of dust and debris. Dust in the atmosphere of an exoplanet can affect our ability to accurately measure the planet's composition, temperature, and habitability. However, dust can also provide valuable information about the planet's environment. By analyzing the light that passes through or reflects off a planet's atmosphere, scientists can learn about the types of gases present, the presence of potential clouds, and the overall composition of the planet's surface. The study of cosmic dust is not limited to its role in the formation of stars and planets. It also plays a significant part in our understanding of the origins of the universe itself. The distribution of dust throughout space provides clues about the conditions that existed in the early universe. By examining the isotopic composition of dust particles, scientists can gain insight into the types of stars that existed in the early stages of the universe and the processes that led to the creation of heavier elements. Thus, cosmic dust is not only a byproduct of stellar processes, but also a vital component in the ongoing evolution of the universe. It contributes to the birth of stars, the formation of planets, the chemistry of atmospheres, and the dynamics of galaxies. It plays a role in the destruction of old stars and the creation of new ones, and it affects the very way we observe the universe. Cosmic dust is an integral part of the universe's life cycle, a cosmic thread weaving through the fabric of space and time, carrying with it the essence of the stars, the galaxies, and the planets that define our universe. As our technology continues to advance, our understanding of cosmic dust will undoubtedly deepen. Future space missions, such as those aiming to capture samples from asteroids or comets, will provide new opportunities to study the composition of dust and debris from even farther reaches of the cosmos. The more we learn about these particles, the more we uncover about the universe itself, its past, present, and future. The mysteries of space dust and cosmic debris are far from being fully understood, but as we continue our journey through the cosmos, we are certain to uncover new and exciting revelations about the role these particles play in shaping the universe. As our exploration of cosmic dust continues, it becomes increasingly clear that these minuscule particles, though seemingly insignificant in isolation, play a major role in shaping the destiny of entire galaxies, star systems, and planetary bodies. Their influence stretches far beyond the formation of stars and planets, affecting the fundamental processes that govern the evolution of the universe. A major consideration in studying cosmic dust is its connection to the broader field of astrophysics. Dust serves as a tracer for a variety of cosmic processes. When scientists study the distribution of dust within a galaxy or nebula, they can make inferences about the distribution of gas, the presence of active star-forming regions, and even the age of certain celestial structures. This is particularly important when attempting to understand the evolution of galaxies over cosmic time. By studying the dust within distant galaxies, scientists can discern how the properties of galaxies change as they age and evolve. In addition, cosmic dust plays a critical role in the interactions between stars and the interstellar medium, the vast, diffuse region of space that exists between stars. The particles that make up cosmic dust are often ionized by the radiation of nearby stars, and this ionization affects the physical properties of the surrounding gas. These interactions are key to the formation of molecular clouds, the birthplaces of new stars. As radiation from nearby stars ionizes the dust particles, it helps to trigger the collapse of these clouds, which leads to the creation of new stars and ultimately, the formation of new planetary systems. Without the presence of cosmic dust and its interactions with starlight, this process would be much less efficient. The complexity of cosmic dust is also evident in the way it interacts with light. Dust has the remarkable ability to absorb and scatter light across different wavelengths. This scattering process, called extinction, can dim the light from distant stars, making them appear less bright and, in some cases, completely obscured. This effect has profound implications for the study of distant galaxies, particularly those at the edge of the observable universe. When observing distant galaxies, astronomers must account for the dust within those galaxies and in the space between them. Without considering this dust, the true properties of these far-off galaxies could remain hidden from view, preventing us from fully understanding their structure, composition, and behavior. Interestingly, cosmic dust doesn't only block visible light, it can also absorb ultraviolet and infrared radiation, emitting its own radiation in the process. This phenomenon, known as thermal emission, occurs when the dust absorbs energy from nearby stars or other sources and re-emits it in longer wavelengths. This emitted radiation can be detected by infrared telescopes, which allow astronomers to peer through the dust clouds that obstruct visible light. The study of thermal emission from cosmic dust has opened up new avenues for understanding the hidden structures within galaxies, including star-forming regions and the central regions of galaxies that are otherwise obscured. One of the most remarkable discoveries in the study of cosmic dust has been the identification of organic molecules within dust grains. These organic molecules, which include amino acids and other complex carbon-based compounds, provide a potential link between dust and the origins of life. While the exact role of cosmic dust in the formation of life on Earth remains a topic of debate, there is growing evidence to suggest that these particles may have played a role in delivering the necessary ingredients for life to our planet. In fact, some scientists believe that organic molecules found in interstellar dust could have been delivered to Earth by comets or asteroids, contributing to the chemical processes that eventually led to the emergence of life. Moreover, the study of cosmic dust has provided valuable insights into the origins of the solar system. By analyzing the composition of dust particles in the solar system, scientists have been able to learn about the conditions that existed in the early solar nebula, the cloud of gas and dust from which the sun, planets, and other objects in the solar system formed. The dust particles that remain today serve as relics of this ancient material, preserving a record of the conditions that existed 4.5 billion years ago. Through detailed analysis, researchers can determine the chemical composition of these particles, offering clues about the types of elements that were present in the early solar system and the processes that led to the formation of planets like Earth. Beyond our solar system, cosmic dust also plays a key role in the study of exoplanets. As previously mentioned, dust particles in the atmospheres of distant exoplanets can obscure our ability to fully characterize these planets. However, dust can also provide valuable information about the nature of exoplanetary environments. For example, the study of exoplanetary dust can offer clues about the planet's atmosphere, surface conditions, and even its potential habitability. In some cases, dust in the atmosphere of an exoplanet can reveal the presence of specific gases or minerals, which may provide insight into the planet's climate or the potential for life. As telescopes and observational technologies continue to improve, our ability to study cosmic dust is only going to increase. With advanced instruments capable of observing dust in new wavelengths and with greater sensitivity, scientists are uncovering more about these particles than ever before. The discovery of cosmic dust clouds and their effects on starlight has revolutionized our understanding of the universe's structure and the processes that govern its evolution. From the birth of stars to the formation of planets, from the obscuration of distant galaxies to the potential for life beyond Earth, cosmic dust is intricately connected to nearly every aspect of astrophysical research. In the future, missions that sample interstellar dust could provide direct evidence about the composition of the material that exists in the vast regions of space between stars. These particles may hold the key to understanding the origin of the solar system, the conditions necessary for life, and the broader evolution of the universe itself. As our understanding of cosmic dust deepens, we will continue to uncover new and exciting revelations about the universe and our place within it. Cosmic dust and debris are more than just a collection of particles floating through space. They are a critical element in the cosmic cycle that shapes the birth and death of stars, the formation of planets, and the overall structure of the universe. These tiny grains, rich in chemical diversity, play a profound role in the dynamics of galaxies, the evolution of planetary systems, and the very chemistry of life itself. While we have only scratched the surface of understanding these particles, their influence is already evident in nearly every facet of astrophysics, from the formation of galaxies to the potential for life on other worlds. In essence, cosmic dust is a cosmic signature, a record of the processes that have shaped the universe for billions of years. Through its study, we gain a deeper understanding of the forces that govern the universe and how everything, from stars to planets to life itself, is interconnected. Cosmic dust may be small, but its impact is enormous, shaping the cosmos in ways that continue to unfold before our eyes. As we continue our journey into the stars, the study of cosmic dust will undoubtedly reveal even more about the intricate workings of the universe, offering us a glimpse into the cosmic cycles of creation, destruction, and rebirth that govern the universe at every scale. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.